Hello, Dr. Grissom. This is Benjamin Broadwolf. My partner is Hannah Gray, and we will be presenting on quantum computing. So when I describe quantum computing, the breakdown will be a general background, a history of quantum computing, and Hannah will do the applications and what it's useful for. While I describe what quantum computing is, I will split it into three key features of how quantum computing functions and how it separates itself from normal computers. Key element 1. What is a bit versus a qubit? Element 2. How superposition works and why it is important. And lastly, entanglement and what that functions as in a quantum computer. Let's dive deeper into bits versus qubits. A bit in a regular computer is like a light switch in your house. It can be either on, which represents a 1, or off, which represents a 0. Every piece of information a regular computer possesses is made up of many bits, all being either on or off. When you type a letter A on your phone or computer, that letter gets translated into a series of bits using something called binary code, a language that a computer understands. In binary, the letter A is represented by the number 65, and in binary, 65 is written as 0, 1, plus 5 zeros, and a 1. Now imagine if your light switch could be on, off, or both at the same time. That sounds rather impossible, right? But that's what a qubit can do. And it's actually accomplishing in real functional quantum computers today. Sorry, that is functioning in real quantum computers today. This is called superposition, where a qubit can be a 1, a 0, or both at the same time, and actually a ratio of the two as well. So let's talk more about superposition. Now here's where quantum mechanics come in. Superposition is a special quantum property that allows qubits to exist in multiple states at once. It's as if a coin can be both heads and tails at the same time. In fact, it's a mix of both, that is, until we observe or measure it. When we observe or measure a qubit, its superposition ends, and it collapses into one definite state, either 0 or 1. This is called wave function collapse, and it's a key aspect of quantum mechanics. Until measurement, the qubit is in a mixed state, holding both possibilities at once. But as soon as we check, the qubit must decide on a single value. This collapse is not deterministic. It's governed by probability. The likelihood of the qubit collapsing to 0 or 1 depends on its probability amplitudes. These amplitudes are squared to give the actual probabilities of measuring each state. For example, if a qubit state is 60% likely to be 0, after measurement, there's a 60% chance we can find a 0, and a 40% chance we'll find a 1. The next key element of quantum computing is entanglement. Before particles become entangled, they are in a state of superposition, meaning each particle can exist in multiple possible states at once. When particles become entangled, the possible states of these particles are no longer independent of each other. Instead, their states become correlated or parallel. This means that the measurement of one will reveal information about the other. If qubit A is measured and found to be in the 0 state, qubit B will immediately be in the 0 state as well. If qubit A is found in the 1 state, qubit B will be in the 1 state too, no matter the distance between them. This communication between photons is instantaneous, but no actual signals travel between them. This is just one of the odd qualities that entangled photons have. In 2017, researchers in China used entanglement to set a distance record by sending entangled photons between Earth and a satellite 1,200 kilometers away. The photons remained entangled even across a great distance, confirming the strange nature of quantum mechanics on a large scale. So let's talk about the history of quantum computing. Quantum computing as a concept was first proposed in the 1980s, but there are many more important milestones that were recorded. In 1981, physicist Richard Feynman suggested the idea of quantum computers at a conference. He pointed out that classical computers struggle to simulate quantum systems efficiently, and theorized that a computer based on quantum mechanics could perform these simulations far more efficiently. Erwin Schrödinger and Werner Heisenberg were the key figures in developing the theory of quantum mechanics. Their work laid the groundwork for understanding the quantum behavior of particles, which is the foundation for quantum computing. In 1926, Erwin Schrödinger formulated a wave equation that accurately calculated the energy levels in the electrons in an atom. In 1933, Schrödinger won the Nobel Prize in Physics because of his assumption that matter could be regarded as both particles and waves. Werner Heisenberg's name will always be known for his theory of quantum mechanics, which was published in 1925 when he was only 23 years old. He also got a Nobel Prize in Physics in 1932. So how will quantum computing So how will quantum computing impact different fields? First up, we have software development. Quantum computing will change software by introducing quantum algorithms like Shor's and Grover's, which solve problems much faster. New quantum programming language will come out, and cryptography will probably require quantum-resistant encryption to protect data. This is already seen in many financial institutions like JP Morgan Chase and Visa. We have hardware development. Quantum processors use qubits and entanglement, enabling parallel computations. This will lead to the development of specialized quantum hardware that outperform classical CPUs and GPUs, and new hybrid systems containing both. In the picture on the right, we can see NVIDIA has already been dipping their feet in the world of quantum computing. For my choice, I chose the pharmaceutical industry. Quantum computing will most likely revolutionize drug discovery by being able to simulate molecular structures more efficiently. And this is going to speed up drug development and lead to innovations in treating diseases. For my research paper, I looked at Don Monroe's quantum computers and the universe. So what problem were they solving? Monroe takes a look at the potential of quantum computers, and he addresses how it's used to tackle some of the problems that classical computers have with understanding the universe. One issue Monroe looks at is how quantum computers can be used to tackle problems in physics and cosmology. In other sections of his journal, he emphasizes breakthroughs in quantum algorithms, like Shor's algorithm for factoring numbers, which demonstrates quantum superiority in specific tasks. This is very encouraging for the world of quantum computing, where progress is not easy to come by. Because quantum computers are still not very old in the grand scheme of classical computers, as they emerged in the 1980s. Monroe also discusses applications in physics where quantum algorithms can be used to simulate real-world problems that are beyond the reach of traditional computers. One example in the text is where he uses quantum computers to explain the behavior of electrons in a molecule, where he claims that classical computers have no reach to when it comes to that topic. I will finish by reading this quote from Monroe. Ideas for quantum computing change the way we think about space and time. So this is my works cited page. I was leaving this room here for Hannah. And this is my research paper link down here, and this is my research paper citation.